All right. So today we are talking about Chapter 13, Section 2. We're going to focus in on the ideal gas law today. So this has a fundamental little difference from the gas laws that we learned yesterday. The key difference as far as what problems are going to look like is there isn't going to be a change, right? So the problems you did on the last assignment, you had a gas at a set of conditions and you changed one of those conditions to find out what the change in the other condition would be. Here with the ideal gas law, we'll just be looking at a gas, and based on the set of conditions that you have, you'll be able to know the rest just from that. And where this lumps in is with our good friend Avogadro again. So hopefully you recognize his name from a number of chapters ago. Avogadro is our friend that brought us the mole, and I hope you remember Avogadro's number of 6.02 times 10 to the 23rd. Remember, that was the number of things in a mole. Well, in this section, we're going to delve into what a mole of any gas, what properties you can expect in that. Okay, and so we'll specifically look at something called molar volume, which is just simply the volume of one mole. That's what molar volume is. The volume that one mole of a gas takes up. And then standard temperature and pressure, you learned last chapter. In chapter 12, I taught you STP. Remember, that is 0 degrees Celsius and 1 atmosphere of pressure. Those are your standard temperatures and pressures. So a lot of this you do know. We just have to figure out how it all combines together. So let's keep going. So Avogadro's principle stated that equal volumes of gas, if they are at the same temperature and pressure, must contain the same number of particles. This idea is what gave way to his understanding of molar volume, right? So let's look at this. If each of these canisters of gases are definitely the same volume, and I'm telling you they're at the same temperature and pressure, that means I have the same number of particles. And if you look at our model, you can see that that's true. There's 5 particles of carbon dioxide here. There's 5 atoms of helium there. And there's 5 molecules of oxygen there. Same volume, same number of particles. So this led to his concept of molar volume. And he said that of any gas, 1 mole, if it is at 0 degrees Celsius and 1 atmosphere, and we know that that 0 degrees and 1 atmosphere is what we call STP, if my gas is at those conditions and I have 1 mole of that gas, then it must occupy 22.4 liters. And this has held constant. This is what's known as the molar volume. The volume 1 mole takes up. And what this does is it gives us a new conversion factor. Just like we had molar mass in stoichiometry, which was the mass that 1 mole has, we now have molar volume. So the conversion factor then becomes 1 mole is equal to 22.4 liters. And remember, likewise, a conversion factor can be the reciprocal, right? 22.4 liters is the same as 1 mole. And so now with this relationship, if our gases are at standard temperature and pressure, we can determine how many moles we have if we know the liters, or how many liters we have if we know the moles. So that's going to come in even more important on Friday when I teach you that lesson as well. All right, let's look at a problem. The main component of natural gas used for home heating and cooking is methane. There's the molecular formula. Methane. Calculate the volume that 2 kilograms of methane gas will occupy at STP. Here's that key. If we're at STP, what volume do we know 1 mole of gas occupies? That's right, 1 mole is equal to 22.4 liters. So we got to keep that in mind. We can only use this because we're at STP though. So what do we need to know? We need to know how many moles. We don't have that though. We have kilograms. Well, let's go back to first semester. Do you know how to convert kilograms to grams? Well, think of that stair step that I taught you, right? So to go from kilograms to grams is 3 jumps to the right. We just have to move our decimal, and we're going to get 2,000 grams. Okay, well, if we have 2,000 grams, can we convert 2,000 grams to moles? You guys know how to do this, right? We want moles, so put our words in first. Moles, what we're trying to find. Grams is what we want to cancel out. How many moles is equal to how many grams of methane? Well, this is where that molar mass comes in, right? We look at the periodic table. Carbon has 12 grams, hydrogen has 1, but we have 4 of them. So this is a total of 16 grams. So all we have to do is divide 2,000 by 16. And I don't have my calculator on my phone right here with me, so I'm going to ask my husband to do the math for me. Ken, can you plug in 2,000 divided by 16, please? You get 125 moles. Keep the calculator up. I need another calculation. All right, so if we've got 125 moles, we now can use this conversion factor to help us find the volume, the liters. Again, 125 moles. Set up your conversion factor. Moles is going to go on the bottom because that's what we want to cancel out. Liters is what we want to find. That goes on top. Well, how many liters equal how many moles? I hope you said 22.4 liters equal 1 mole. So that means we're going to multiply. Can you multiply 125 by 22.4? And I get 2,800 liters. And that would be the correct answer. All right, let's keep going. Oh. I'm running the PowerPoint from my iPad, so it's a little different. Okay, well, if you look here, this PV over T, you should recognize from yesterday's lab. This is the combined gas law. All right, this is where we combined all 3 of our general gas laws. By seeing that this is an equivalence there, we can say that pressure, volume, and temperature are always equal to a constant. And it's this mathematical understanding that takes us to the ideal gas law, because we are going to look at what that constant is. So the ideal gas law, here is the formula you need to remember. PV equals nRT. P stands for pressure, V stands for volume, T stands for temperature. Now this lowercase n represents the number of moles. So if you know the number of moles, you would just plug it in for n. However, R is what we call the ideal gas constant. Now, the ideal gas